Tonight, the James Webb Space Telescope sent back a number that was wrong. Not wrong in the sense of a malfunction. Not wrong in the sense of a broken instrument. Wrong in the sense that the universe returned a result that the model said was not supposed to happen. A rocky planet, roughly twice the mass of Earth, orbiting its star at less than 1% of the distance between our planet and the Sun, should have been a bare rock, stripped clean by radiation. No atmosphere. Just a scorched, airless surface baking in unbroken starlight. The temperature the telescope measured was not what a bare rock would produce. It was cooler. Nearly 1,700 degrees Fahrenheit cooler than the models predicted. And that gap, that single temperature discrepancy, cracked open a discovery that nobody expected to find on a planet like this. The planet is called TOI 561b. It is 280 light-years from Earth. It orbits its star once every 10.56 hours. And James Webb has just confirmed it has an atmosphere that should not exist. But here is the part the title promises. The more you learn about this planet, the more disturbing it becomes. Not because of any single fact, because of what each fact does to the one before it. Every layer of this discovery makes the previous layer stranger, and by the end of tonight, you will understand why the scientists who studied this data described it with the words, "What the heck is this?" Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. In May of 2024, engineers pointed the James Webb Space Telescope at a star 280 light-years from Earth and told it to watch. Not to glance. Not to make a quick measurement and move on. To watch continuously for 37 hours and 18 minutes. During that time, JWST tracked the brightness of the star-planet system without interruption, capturing 4 complete passages of TY 561b behind its host star in sequence. The technique is called a secondary eclipse observation, and understanding it is essential to understanding why what came back was so significant. When a planet orbits a star, it spends part of its orbit in front of the star from our perspective, and part of its orbit behind the star. When the planet moves in front of the star, it blocks some of the star's light, and the total brightness of the system drops slightly. This is called a transit, and it is one of the main ways we discover exoplanets at all. But the secondary eclipse is different. That is the moment when the planet moves behind the star and disappears from view entirely. Think of it this way. If you are holding a lit candle in front of a lamp, you see both sources of light together. When the candle moves behind the lamp, you lose the candle's light and see only the lamp. The difference in brightness between the two measurements, candle plus lamp and lamp alone, tells you exactly how bright the candle was. For TOI 561b, the candle is the planet, the lamp is the star. By measuring the tiny drop in total brightness each time the planet disappears behind its star, the James Webb Telescope could isolate the infrared light being emitted by the planet itself. And from the intensity of that emission, the team could calculate the temperature of the planet's sunlit side directly. The measurement required precision that would have been impossible from any earlier facility. Earth's own atmosphere absorbs large portions of the infrared spectrum, making this kind of observation impractical from the ground. Earlier space telescopes lacked the cold operating temperature and the infrared sensitivity that Webb's instruments provide. Webb orbits at the L2 point, a gravitational balance point approximately 1 million miles from Earth, where its sunshield keeps the instruments at temperatures near absolute zero. This cold operating environment is what makes the faint infrared signal of a rocky planet detectable at all. The NISPEC instrument, the near-infrared spectrograph, recorded 4 consecutive secondary eclipses over those 37 hours. Each one added to the dataset. Each one confirmed what the previous one suggested. The combined measurement produced a temperature for the planet's dayside that the team could quote with confidence. That temperature was approximately 3,200 degrees Fahrenheit, about 1,800 degrees Celsius. Now, that is an extreme number by any ordinary standard. It is roughly twice the temperature of lava flowing from a volcano on Earth. It is hot enough to melt most metals. It is a surface temperature that no living thing could approach and survive. But it was not the number that disturbed the team. What disturbed them was the number they had expected to find. For a bare rock at TOI 561b's distance from its star, the equilibrium temperature, the temperature produced by the star's radiation alone, without any atmosphere to redistribute heat, should approach approximately 4,900 degrees Fahrenheit, about 2,700 degrees Celsius. The difference between the expected number and the measured number is approximately 1,700 degrees Fahrenheit, 900 degrees Celsius. This gap is not a rounding error. It is not within any reasonable measurement uncertainty. It is a signal. A clear, confident signal that something on this planet is moving heat away from the sunlit side. Something is absorbing radiation, carrying energy, spreading warmth to regions that would otherwise not receive it. The most straightforward explanation, the one that best fit the data when the team tested multiple models against the observations, was a thick, volatile-rich atmosphere wrapping the planet and distributing heat across its surface. Lead author Joanna Teskey of Carnegie Science used the word confident. Co-author Anjali Piete of the University of Birmingham said, "We really need a thick, volatile-rich atmosphere to explain all the observations." That was December 2025, a peer-reviewed result in the Astrophysical Journal Letters. The strongest evidence yet for a rocky exoplanet atmosphere beyond our solar system. But the temperature gap was only the beginning, because to understand why a confirmed atmosphere on TO 561b is disturbing, you first need to understand what kind of planet this is. And that is where things start to become genuinely unsettling. The secondary eclipse technique deserves to be understood fully because it is the foundation of everything that follows. Without grasping how the measurement was made, the result cannot be properly evaluated. When the James Webb Telescope observes a star-planet system using this method, it is not taking a photograph. It is not resolving the planet as a separate dot of light. The planet is far too small and far too close to its star for any current telescope to image it directly as a distinct object. What the telescope is doing is something more subtle. It is measuring the total light output of the system as a whole, star and planet combined, and tracking how that total changes with time. During a secondary eclipse, the planet passes behind the star. For the duration of the eclipse, the planet's own light contribution is removed from the measurement. The telescope sees only the star. Before and after the eclipse, it sees both. The difference between those two measurements, carefully calibrated and corrected for instrumental effects, is the planet's own emission. How much infrared light is the planet giving off? That quantity, measured across multiple wavelengths, tells you the temperature. The precision required is extraordinary. TOI 561b is a rocky world roughly 1.5 times Earth's radius. Its total light output is a tiny fraction of its host stars. The secondary eclipse signal, the drop in brightness when the planet disappears, is measured in parts per million. Detecting it requires not just a sensitive instrument, but a stable one. Any variation in the telescope's own pointing, temperature, or detector response over the 37 hours of the observation could masquerade as a planetary signal. JWST's stability at the L2 point, shielded from the sun by its enormous 5-layer sunshield, is what makes this kind of measurement possible. The fact that 4 consecutive secondary eclipses were captured in a single observation run is also significant. A single eclipse could be questioned. Was there an instrumental artifact? Was there a stellar flare that affected the measurement at that moment? 4 eclipses, each consistent with the others, each returning the same temperature signal, constitute a robust detection. The probability of 4 independent instrumental artifacts conspiring to produce the same result is negligibly small. This is the quality of evidence behind the conclusion. Not a hint, not a tentative suggestion, a confident measurement made 4 times in sequence by the most capable infrared telescope ever placed in space. The 37-hour observation window also carries its own significance beyond the technical requirements. When you track a system for 37 continuous hours, you are not just collecting data on the 4 eclipses. You are building a record of the entire system's behavior over multiple orbital periods. TOI 561b's orbit is 10.5 to half 6 hours long. 37 hours encompasses nearly 3.5 complete orbits. The brightness of the system at every orbital phase, not just the eclipse moments, is recorded. This means the data contain the seeds of a future phase curve analysis. A phase curve measurement tracks how the total brightness of the star-planet system changes throughout the planet's full orbit, from the maximum dayside contribution when the planet is between the observer and the star, through the eclipse when the planet vanishes, and through the nightside portion of the orbit when the cooler nightside faces the observer. The phase curve contains information about the temperature distribution all the way around the planet. The current publication focused on the secondary eclipse temperature measurement, which is the strongest signal in the dataset. The full analysis of the complete observational record, including the phase curve, is ongoing. When that analysis is complete, it may reveal information about the temperature of the night side, the degree of heat redistribution from day to night, and the atmospheric structure in ways that the eclipse measurement alone cannot provide. This is the layered nature of a high-quality JWST observation. The initial result answers one question clearly. The same dataset contains the foundation for future answers to other questions. The observation of TO5561b in May 2024 produced more data than the December 2025 paper could fully analyze. The field will continue to extract understanding from it for years. In our solar system, there are rules. Not arbitrary rules. Not arbitrary rules. Physical rules, grounded in decades of observation and theory. Rules about which planets can hold onto atmospheres and which ones cannot. Mercury, which is small and close to the Sun, has no significant atmosphere. The Sun's radiation and solar wind have stripped it clean over billions of years. Mars, which is larger than Mercury but still relatively small and exposed, has an atmosphere so thin it exerts less than 1% of Earth's surface pressure. Venus, which is roughly Earth's size, has a thick atmosphere, but Venus is much farther from the Sun than TOI 561b. The rules say that small rocky planets orbiting very close to their stars lose their atmospheres. The radiation is too intense. The planet's gravity is too weak to hold gas against that pressure. The atmosphere erodes away. TOI 561b violates those rules at every level. It is a super-Earth. Its radius is approximately 1.4 times the radius of Earth. Its mass is approximately 2 Earth masses. By the standards of rocky planets, it is on the smaller end of what can be considered a super-Earth. It is not a large world. It does not have an unusually strong gravitational grip. It is not a Neptune-sized planet with the mass to hold a deep gas envelope. Its orbit is roughly 0.01 astronomical units from its star. 1 astronomical unit is the average distance between Earth and the Sun. The distance between Mercury and the Sun is about 0.39 astronomical units, TOI 561. B orbits at 1/40th of Mercury's distance from its own star. Put another way, if you placed TOI 561b in our solar system, it would be orbiting roughly 1 million miles from the Sun. Earth is 93 million miles from the Sun. This planet would be tucked inside the Sun's corona, the outermost layer of the solar atmosphere, existing in an environment of radiation pressure and particle flux that would strip any ordinary atmosphere in geological time. Its orbital period is 10.56 hours. 1 year on this planet is less than half an Earth day. Earth completes one orbit in 365 days. TOI 561b completes an orbit in less than 11 hours. For every single day on Earth, this planet has gone around its star more than twice. This category of planet has a name, an ultra-short period planet. The definition is straightforward: any rocky world with an orbital period shorter than 1 Earth day. These planets are studied extensively because they are extreme test cases, environments so hostile that they push our models to their limits. The received wisdom in planetary science, the working assumption built into atmospheric models, is that ultra-short period rocky planets with masses like TOI 561b should not retain atmospheres on any meaningful timescale. Stellar radiation should strip their gaseous envelopes away. High-energy photons should ionize the atmospheric molecules. Solar wind should sweep them off the surface. The planet should be left as a bare, hot rock. TOI 561b should be a bare, hot rock. JWST1b should be a bare, hot rock. JWST says it is not. Every property of this planet argues against the existence of its atmosphere. Its size argues against it. Its proximity to its star argues against it. Its orbital period argues against it. The intensity of radiation it receives argues against it. The intensity of radiation it receives argues against it. The models argue against it. And yet JWST stared at it for 37 hours, measured its temperature 4 times from 4 separate secondary eclipses, and found a number that only makes sense if an atmosphere is there. That is the first layer of the disturbance. But the next layer asks a different question. Not whether the atmosphere is there, it clearly is. The next question is, what does the surface of this planet actually look like underneath it? The significance of the size and orbital parameters of TOI 561b becomes clearer when placed against the full population of known exoplanets. As of late 2025, astronomers have confirmed the existence of roughly 6,000 exoplanets orbiting stars beyond our own Sun. This population spans an enormous range of sizes, from worlds smaller than Earth to gas giants many times the mass of Jupiter. It spans an enormous range of orbital distances, from planets that orbit their stars in a matter of hours to planets that orbit in hundreds of years. Within this population, ultra-short period planets are a distinct and well-studied category. They are common enough to have been found around many types of stars. They are studied specifically because their extreme environments make certain physical processes observable at amplified scales. Atmospheric loss, for instance, happens faster on these worlds, which makes it easier to detect and measure compared to planets farther from their stars. The standard expectation for rocky ultra-short period planets with masses in the range of TOI 561b, roughly 1 to 5 Earth masses, is atmospheric depletion on timescales of millions to a few hundred million years. This is derived from models that include photoionization by stellar extreme ultraviolet radiation, heating of the upper atmosphere to temperatures at which gas molecules reach escape velocity, and the pressure of the stellar wind pushing against the atmospheric envelope. These processes are not speculative. They have been observed operating on planets in our own solar system. Mars lost its atmosphere primarily through atmospheric escape, aided by the absence of a strong magnetic field to deflect the solar wind. Earth's early atmosphere was different from its current one, partly because atmospheric escape removed lighter gases like hydrogen over geological time. The physics is well understood at the qualitative level. The quantitative question, how fast does it happen for a planet like TOI 561b around a star like TOI 561, is where the models diverged from observation. The models said fast enough that after 10 billion years, nothing should remain. The observation said something remains. The physics is right, the rates are wrong. And finding out why the rates are wrong is one of the central scientific goals that this discovery has opened. The history of how ultra-short period planets were first understood helps clarify why the atmospheric expectation was what it was. When the first ultra-short period planets were discovered by ground-based transit surveys in the early 2000s, and then by the Kepler Space Telescope in the 2010s, they were recognized as a distinctive category requiring specific physical explanation. Why do rocky planets exist at these extreme orbital distances? The leading explanation involves orbital migration. These planets likely did not form where they are. They formed farther from their stars and gradually spiraled inward through gravitational interactions with the protoplanetary disk of gas and dust in which they originally developed. This inward migration brought them to their current positions, typically after the disk had dissipated, which is why they did not spiral all the way into their stars. Once recognized as migrated worlds, the question became, what does migration leave behind in terms of planetary properties? A world that formed at a larger orbital distance and migrated inward would have had a different temperature history and a different volatile inventory than a world that formed in place at its current location. The migration story was part of the original context for understanding these planets. What it did not obviously solve was the atmosphere question, whether a migrated world would arrive at its ultra-short period orbit with volatiles intact, and whether it could retain them against the stellar environment at its new location remained a question the models addressed by saying, probably not, over long timescales. The migration might deliver a volatile-rich world to a close orbit, but the stellar environment would strip the atmosphere in geologically short order, TY561b's 10 billion-year-old star means the planet has had 10 billion years at its current location. Whatever migration history it had is ancient. The current environment has been operating on it for so long that the initial conditions of migration are largely irrelevant. What matters is what it has been doing since it arrived, and the answer is maintaining an atmosphere the model said it could not. There is a phenomenon called tidal locking, and understanding it is necessary to understand what TY561b has become. When a planet orbits close enough to its star, the star's gravity creates a difference in gravitational pull across the planet's diameter. The side of the planet facing the star is pulled more strongly than the side facing away. This creates a tidal stress across the planet's body, and over time, that stress does something specific. It gradually slows the planet's rotation until the rotation period and the orbital period match. Once they match, one side of the planet faces the star at all times. The rotation and the orbit become synchronized. The planet stops spinning, in the sense that it no longer rotates relative to the star. One hemisphere sees the star forever. The other hemisphere never sees it at all. We have an example of this in our own solar system. The Moon is tidally locked to Earth. The near side of the Moon, the side with the Maria and the craters visible to the naked eye, always faces Earth. The far side, which was entirely unknown until spacecraft photographs in the 20th century, always faces away. The Moon rotates once per orbit, and the two motions cancel out from Earth's perspective. We see the same face every time. For TY561b, the same process has occurred, except the locking body is a star rather than a planet. The planet orbits so close that the timescale for tidal locking is millions of years, far shorter than the system's age. TY561b is almost certainly tidally locked to its host star. What this means in practical terms is this. One side of the planet is in permanent noon. The star hangs directly overhead, motionless, for what would be the entire history of the planet. The sunlit side has been receiving continuous stellar radiation without interruption for as long as the planet has orbited in this configuration. There is no morning, there is no afternoon, there is no day transitioning into evening and then into night. There is only a single unbroken blaze of light on one hemisphere and a single unbroken darkness on the other. On Earth, day and night alternate every 24 hours. The heat of the day is moderated by the cool of the night. The tropics are warm, but they are not scorched, because the atmosphere redistributes heat and because the sun does not stay overhead. Seasonal tilt varies the solar input. Temperature cycles exist. Life has evolved to use those cycles to depend on them. On TY561b's day side, none of this applies. The star does not set. The temperature does not cycle. The radiation does not cycle. The radiation does not vary. The sunlit hemisphere has been in this state since long before our solar system formed. If you could somehow stand at the center of the day side and look up, you would see the star filling a portion of the sky unmoving at all times, at an intensity that would make the sun seem dim in comparison. The light would be relentless. The heat would be absolute. Now ask the question, what happens to rock when you expose it to that kind of heat, at that intensity without any break for billions of years? The answer is the next layer. The phenomenon of tidal locking has a deeper consequence for TY561b that goes beyond the simple division of the planet into a permanent day side and a permanent night side. On a tidally locked planet, the atmospheric circulation is profoundly different from anything in our solar system. On Earth, the atmosphere is driven by differential heating between the equator and the poles, by the Coriolis effect from planetary rotation, and by the annual cycle of the seasons. Weather systems form, evolve, and dissipate on timescales of days to weeks. There is a constant stirring of the atmosphere driven by temperature differences that vary predictably with latitude, season, and time of day. On a tidally locked planet, the primary temperature difference is not equator to pole. It is day side to night side. The hottest point on the planet is the substellar point, the spot directly beneath the star. The coldest point is the antistellar point, directly opposite on the night side. Between them, the temperature changes dramatically across the terminator, the boundary between the day and night hemispheres. This creates an atmospheric circulation pattern fundamentally different from Earth's. The dense hot air above the substellar point rises and spreads outward toward the terminator and the night side, driven by the pressure gradient from the heated day side. Cooler air flows back from the night side toward the substellar point along the surface. The overall pattern is not the complex mid-latitude weather systems of Earth. It is a simpler, more direct day-side to night-side heat engine. On TI 561b, these winds are almost certainly supersonic. The temperature contrast between the substellar point and the night side drives pressure differences large enough to accelerate air to high speeds. Models of similar worlds consistently predict atmospheric wind speeds reaching several kilometers per second, faster than the speed of sound on Earth. It is these winds, circulating rapidly from the hot day side toward the cooler night side, that carry the heat which produces the cooler than expected dayside temperature JWST measured. The atmosphere is not just present, it is dynamically active, moving heat across the planet at speeds that nothing in our solar system matches, sustained by the locked geometry of a world that has been doing this for 10 billion years. The comparison between the Moon's tidal locking to Earth and TOI 561b's locking to its star is illuminating. But the differences between the two cases are as important as the similarities. When the Moon became tidally locked to Earth several billion years ago, the process took tens of millions of years. The Moon is roughly 400,000 kilometers from Earth on average. The tidal forces that produce the locking were relatively modest compared to what a star exerts on a close orbiting planet. For TOI 561b, the tidal forces are far stronger. The planet is roughly 1.6 million kilometers from its star, approximately 4 times the Moon's distance from Earth, but orbiting a star enormously more massive than Earth. The tidal force scales with the mass of the locking body and inversely with the cube of the distance. The result is that the timescale for TOI 561b to become tidally locked was millions of years rather than billions, and the process was completed long ago. The permanence of the locking has implications for the surface geology. On Earth, the rock cycle is partly driven by the day-night temperature cycle. Thermal expansion and contraction of rocks contributes to weathering and erosion. The slow alternation of heating and cooling helps break down the surface over geological time. On the day side of TOI 561b, there is no such alternation. The temperature is constant. There is no thermal cycling. The surface, insofar as it is a liquid rather than a solid, is in a state of constant, uniform heating. The only variation in the surface environment comes from the internal convection of the magma itself and from the atmospheric circulation above it. On the night side, the temperature is equally constant but dramatically different. If the atmosphere does not extend heat redistribution efficiently to the night side could be cold enough that the surface solidifies. In that case, there would be a permanent solid hemisphere and a permanent molten hemisphere separated by a terminator that has not moved in billions of years. Rock melts, not all at once, not uniformly, but at the temperatures that TOI 561b's day side reaches, well above the melting point of silicate rock. The surface does not solidify the way it does on Earth. On Earth, volcanic rock cools and hardens between eruptions. The ground beneath your feet is solid because the surface is cold enough for rock to maintain its crystalline structure. The crust is rigid. It supports mountains, valleys, oceans, the entire surface architecture of a habitable world. On the day side of TO 561b, the surface is not cold enough for that. Models of this planet's surface, developed in the context of the JWST observations and supported by the temperature measurements, describe the day side as likely hosting a global magma ocean, not a lava lake in a volcanic crater, not a localized region of melted rock. A planetary-scale layer of molten rock covering the entire sunlit hemisphere, possibly extending across the boundary into the night side if the atmosphere distributes enough heat to prevent the night side surface from solidifying. The term magma ocean is not metaphorical. It describes a physical state. When a planet receives enough heat to prevent its surface rock from reaching its solidification temperature, the rock remains liquid. The surface of the planet becomes, in the most literal sense, an ocean, except the liquid is not water. It is molten silicate rock at temperatures exceeding 1,800 degrees Celsius. This state is not unprecedented in our solar system's history. The early Earth had a magma ocean. In the first tens of millions of years after the planet formed, the energy from accretion and from the moon-forming impact kept the surface molten. The ground was liquid rock. The atmosphere above it was a dense, hot mixture of gases cooked out of the melt. Eventually, over tens of millions of years, the surface cooled and solidified. The crust formed. The oceans of water condensed from the cooling atmosphere. The planet settled into something recognizable. That cooling happened because the young Earth moved away from the intense bombardment phase, because accretion ended, because the interior heat dissipated through the surface over time. On TOI 561b, the cooling cannot happen. The star prevents it. Every hour of every year, the day side receives the same intense irradiation that keeps the surface above its melting temperature. The magma ocean is not a phase the planet went through. It is the planet's permanent condition. The day side of this world has been a global ocean of molten rock for billions of years, and it will remain one for billions of years more. Stand above the day side. The surface beneath you would be a slow-churning liquid at temperatures twice as hot as any lava flow on Earth. The atmosphere above it would be dense and hot, a mixture of gases baked directly from the rock, bearing no resemblance to the nitrogen and oxygen envelope that supports life on our planet. The sky, if it could be called that, would be opaque with the vapors of minerals that on Earth exist only as solids. This is what the JWST temperature measurement is describing. Not just a hot planet, a world with a permanent global magma ocean, wrapped in an atmosphere that emerges from that ocean, operating in conditions that have no equivalent anywhere in our solar system. And there is still the question of how the atmosphere survives. The chemistry of a magma ocean atmosphere is unlike anything in the experience of life on Earth. On Earth, the atmosphere is composed primarily of nitrogen and oxygen, with trace amounts of argon, carbon dioxide, and water vapor. This composition emerged over billions of years of geological activity and biological processes. The nitrogen is relatively inert. The oxygen is a product of photosynthesis. The carbon dioxide is cycled continuously between the atmosphere, the oceans, and the crust through geological processes. This is the atmosphere of a planet in a particular kind of equilibrium, one shaped by life as much as by geology. The atmosphere above a magma ocean is shaped by the mineralogy of the rock itself. Silicate minerals, which make up the bulk of rocky planetary crusts, contain silicon, oxygen, magnesium, iron, calcium, and aluminum in various proportions. When these minerals melt and reach temperatures high enough to begin releasing their dissolved volatiles, the gases that emerge depend on the mineral composition and the temperature. At temperatures around 1,800 degrees Celsius, silicon oxides can vaporize, iron silicates can release oxygen and iron vapor. Minerals containing sulfur produce sulfur dioxide. If the magma contains water dissolved in it from the planet's early formation, water vapor is released. The atmosphere above TOI 561b's magma ocean is modeled as a mixture of some combination of these gases: water vapor, sulfur dioxide, oxygen, silicon monoxide, possibly sodium vapor and potassium vapor, which can exist in gaseous form at these temperatures and have been detected in the atmospheres of some hot rocky exoplanets. The exact mixture depends on the composition of the rock and the temperature of the melt. This is not an atmosphere that any living thing has ever breathed. It is not an atmosphere composed of gases selected or modified by biology. It is the raw exhaust of geology, the gaseous phase of rock at temperatures that no organism could survive, suspended above a surface that no foot has ever touched. If you could somehow exist above the terminator of TOI 561b and look across the day side, the sky would not be blue. It would be a thick, hot, opaque haze of mineral vapor, backlit by a star blazing overhead without moving. Its light scattered and absorbed by a column of gas, unlike anything studied in any planetary atmosphere in our solar system. The comparison between the early Earth's magma ocean and TOI 561b's current state is useful, but it obscures an important difference. The early Earth's magma ocean was a transient phase. It formed because of the energy deposited by the giant impacts that occurred during accretion and the collision that formed the Moon. This energy was enormous, enough to melt the entire planet, but it was finite. Once the impact ceased, the planet began to cool. The magma ocean solidified from the surface downward over tens of millions of years until the crust formed and the surface became solid. The cooling was possible because the energy input, after the accretion phase ended, dropped dramatically. The early sun was actually less luminous than it is today. The young Earth was not receiving the relentless irradiation that prevents TOI 561b's dayside from cooling. On TOI 561b, the energy input is not declining. It is not finite. The star will continue delivering the same intensity of radiation to the dayside for billions of years to come. The cooling mechanism that operated on early Earth does not operate here because the heat source is external and permanent rather than internal and diminishing. This is why the term permanent is appropriate when describing TOI 561b's magma ocean. It is not a phase that will end when the heat source runs out. It will persist as long as the star shines, as long as the planet maintains its current orbit, and as long as the planet retains enough mass to have a significant interior. Given the 10 billion year age of the system and the apparent stability of the current conditions, all three of those prerequisites appear to be satisfied for the foreseeable future. The magma ocean is not a feature of TO 561b's youth. It is a feature of its current maturity and its future. An atmosphere above a magma ocean is not like an atmosphere above a rocky surface. On Earth, the atmosphere is largely separate from the solid rock beneath it. Gases enter and leave the atmosphere through volcanic outgassing, through photosynthesis and respiration, through chemical weathering of rocks, but the rock itself is solid, a distinct layer beneath the air. The two phases, solid and gas, are separated by a clear boundary. On TOI 561b, that boundary dissolves. The magma ocean and the atmosphere above it are in constant exchange. The melt is not a static pool. It is active. It churns. Heat from the interior drives convection, warm material rising from below and cooler material sinking. As this happens, dissolved gases within the magma are released. Compounds that exist dissolved in the liquid rock at depth, under the pressure of the overlying melt, reach the surface where that pressure is lower and where the heat drives them into their gas phase. They bubble up, they enter the atmosphere. This process is called outgassing, and it is the mechanism that scientists believe is keeping the atmosphere of TOI 561b alive. The gases likely released from the magma include water vapor, carbon dioxide, sulfur dioxide, and other volatile compounds. These are not exotic chemicals. They are the same gases that terrestrial volcanoes release on Earth, but on Earth they are released episodically from localized volcanic vents in relatively modest quantities compared to the total mass of the atmosphere. The atmosphere was largely built up over billions of years through the slow volcanic seepage and then modified by biological processes. On TOI 561b, the outgassing is not happening from a few volcanic vents. It is happening from the entire dayside surface simultaneously, continuously, from a magma ocean covering a hemisphere. The gas supply is not episodic, it is relentless. At the same time, the star is stripping gas from the top of the atmosphere. High-energy photons ionize molecules. The stellar wind pushes against the atmospheric envelope. Gases that reach the upper atmosphere are lost to space. This process is called atmospheric escape, and it is exactly the process that the models said would have stripped this planet clean long ago. The reason the atmosphere survives is likely that it is being continuously replenished. The magma ocean releases gas from below at roughly the same rate the star strips it from above. The atmosphere is not an ancient relic. It is an ongoing process, a balance between two competing forces, one building and one destroying, maintained in equilibrium by the physics of this unusual world. This is what makes the atmospheric composition still uncertain. The team could identify that an atmosphere was present from the temperature measurement. They could conclude that it must be thick and volatile-rich to produce the degree of dayside cooling they observed. But the specific molecules, the exact chemical fingerprint of what those gases are, requires additional observations. The composition is modeled rather than directly detected. Future JWST observations, pointed at the system for longer and at different wavelengths, may be able to identify specific molecular absorption signatures and tell us what this atmosphere is actually made of. For now, what we know is this: there is a thick gaseous envelope above a global magma ocean, being actively produced by that magma ocean, surviving against a constant stripping force from the star above. The system is not in equilibrium in the way a planet with a stable ancient atmosphere is in equilibrium. It is in dynamic balance, a constant exchange between rock and air, sustained by an energy source that will not stop. This is disturbing on its own terms. A planet whose atmosphere is its own molten surface, slowly breathing itself into the sky. But none of this is the most disturbing thing about TO561b. That comes when you ask how long this has been going on. The 10 billion year age of the TO561 system is not simply large in the abstract sense that all astronomical numbers are large. It is large in a specific, contextually meaningful way that requires unpacking. The universe itself is approximately 13.8 billion years old. It came into existence with the Big Bang, and for the first several 100 million years it contained no stars and no planets. The first stars formed from the primordial hydrogen and helium of the early universe, and the first generations of massive stars lived fast, died in supernovae and scattered the heavier elements, carbon, oxygen, silicon, iron, into the interstellar medium. It was from this gradually enriched interstellar medium that later generations of stars and their planetary systems formed. TOI 561 formed approximately 10 billion years ago. The universe was about 3.8 billion years old at that point. Stars had been forming for several billion years. But the heavy element enrichment of the universe was less advanced than it is today. The interstellar medium from which TOI 561 formed had a lower concentration of elements heavier than helium. This is recorded in the star's composition, its low iron abundance and high alpha element content. This means TOI 561b formed in the early universe from material that was available at that time. The planet that formed around this ancient star incorporated whatever volatiles were present in the early solar nebula in whatever proportions the early interstellar medium provided. Whether those initial conditions gave the planet a particularly volatile-rich composition, which could sustain a more vigorous outgassing cycle, is one of the open questions the discovery raises. What is certain is that whatever processes formed the planet, and whatever processes have sustained its atmosphere since then, have been operating for more than twice the age of our solar system. The Sun has not yet lived half as long as TOI 561 has been burning. Earth has not yet existed for half the time this planet has been in orbit. In that span of time, while this planet was maintaining its magma ocean and its impossible atmosphere, the following things occurred in our corner of the universe. The solar system formed, the Earth cooled. The first life appeared. Life diversified. Animals evolved complex land ecosystems. Developed the dinosaurs, rose and fell. Mammals diversified. Primates evolved hominins. Diverged from other apes. Modern humans appeared. Civilization developed, and the James Webb Space Telescope was built, launched, and operated for 3 years before finding this planet. All of that, in the time since TOI 561b, has been doing what JWST just observed it doing. The chemical composition of the star carries implications not just for the star's age, but for what the planet is likely made of. Stars and the planets that form around them are created from the same cloud of interstellar material. The composition of the star reflects the composition of the cloud from which the entire system formed. A star with low iron abundance but high alpha element content formed from early universe interstellar medium, before many generations of massive stars had enriched the galactic environment with iron. The planets that formed around this star would have formed from similar material. This means TOI 561b likely has a composition that differs in important ways from the rocky planets in our solar system. Earth formed from a solar nebula enriched by many generations of supernovae. Our planet has a significant iron core and a silicate mantle with a particular chemical signature. TOI 561b formed from material that was less iron-rich and proportionally richer in oxygen, magnesium, and silicon. This compositional difference could affect the volatile content of the planet's interior, The amount of water, sulfur and carbon locked in the rocky material at formation depends on the chemistry of the source material. An early universe rocky planet might have a different volatile inventory than a solar system analog planet, with consequences for the rate and character of outgassing. Whether the specific composition of TOI 561b's progenitor material helps explain why the atmosphere has persisted is unknown. It is one of the variables that the theoretical models will need to explore. If the early universe material from which this planet formed was unusually volatile-rich, that could provide a reservoir of gas that the outgassing cycle has been drawing on for 10 billion years without exhausting. This is speculative, but it is a specific, testable hypothesis, and the chemistry of the host star provides a tool for investigating it. The star that TOI 561b orbits is not young. Most stars studied for exoplanet atmospheres are relatively young or middle-aged because young stars are common and because planetary systems are assumed to be more interesting in their earlier phases. TOI 561, the star at the center of this system, is approximately 10 billion years old. That number requires translation. Our own solar system is approximately 4.5 billion years old. Earth formed 4.5 billion years ago. The Sun ignited 4.5 billion years ago. Life appeared on Earth somewhere around 3.8 billion years ago. The dinosaurs went extinct 66 million years ago. Modern humans have existed for approximately 300,000 years. All of recorded human history spans roughly 10,000 years. TOI 561 is approximately twice the age of our entire solar system. When the Sun first ignited, when the solar system was new and Earth was a ball of cooling magma, and the first amino acids were beginning to assemble in the ancient oceans. TOI 561 had already been burning for 4.5 billion years. It was already as old as our solar system currently is. It had already watched its planetary system form and evolve and settle into whatever configuration it would maintain for billions of years to come. When the first single-celled organisms appeared on Earth, this star was already 9 billion years old. When the dinosaurs walked, it was 9.9 billion years old. When the first modern humans were alive, it was 9.9997 billion years old. The age of this star is written into its chemistry. TOI 561 is iron-poor and rich in alpha elements, oxygen, magnesium, and silicon, which are forged in massive stars during their short lives and scattered through the interstellar medium when those stars explode as supernovae. Stars that formed early in the universe when the galaxy had not yet been enriched by many generations of supernovae tend to have this signature. They contain relatively little iron because the iron-producing generations of stars had not yet lived and died when this star formed. The chemistry of the star itself tells you when in cosmic history it was born. Now apply the models. The models of atmospheric loss for ultra-short period rocky planets say that stellar radiation should strip the atmosphere on timescales of millions to hundreds of millions of years. These models were built from first principles, from our understanding of how stellar winds interact with planetary atmospheres, how high-energy photons ionize gas, how escape velocities compare to the thermal velocities of atmospheric molecules. They are not wild guesses. They are careful, peer-reviewed calculations based on well-understood physics. Those models predict the atmosphere should have been gone within the first 100 million years, or perhaps a few hundred million years at most, of this planet's life. The planet is 10 billion years old. The atmosphere survived not for the time the models predicted, but for roughly 10 to 100 times longer, not by a small margin. By an order of magnitude or more. This planet has been doing something that the models said was physically impossible, and it has been doing it for longer than life has existed on Earth. Nicole Wallach of Carnegie Science put it plainly. Based on what we know about other systems, astronomers would have predicted that a planet like this is too small and hot to retain its own atmosphere for long after formation. Too small, too hot, too old. JWST says it has one anyway. The age of this system is what takes the discovery from surprising to genuinely unsettling. It is not just that TOI 561b broke the rules. It is that it has been breaking the rules for 10 billion years. The universe has been doing something here that our models did not account for, and it has been doing it since before our sun existed. And this is where the title's promise becomes complete, because at every layer of this discovery, The answer to one question opens a harder question beneath it. The temperature was wrong. Why? An atmosphere. The atmosphere should not exist. Why does it? Outgassing from the magma ocean. Why has the magma ocean been able to sustain the atmosphere? The star is still heating it, which means the planet has been in this condition for 10 billion years. How did any of this survive for 10 billion years against the stripping force of the star? We do not know. The history of JWST itself provides important context for understanding why this discovery matters beyond the specific science of TOI 561b. The James Webb Space Telescope was conceived in the 1990s as the successor to Hubble. Its development took decades. The program was over budget and behind schedule for much of its development history. There were moments when it seemed it might never launch. The complexity of the telescope, its segmented mirror, its cryogenic instruments, its folded sunshield that had to deploy correctly in deep space, far from any possibility of repair, made it one of the most technically challenging projects in the history of space science. It launched on December 25, 2021, deployed successfully in all its critical steps, reached the L2 point, cooled to its operating temperature, and began science operations in 2022. The scientific community had prepared an enormous backlog of proposals. Teams had spent years developing observing programs that JWST's capabilities would enable. The telescope time is allocated through a competitive process, and the first years of operation have been filled with programs targeting everything from the formation of the first galaxies in the early universe to the composition of distant exoplanet atmospheres. The TOI 561b program, which observed the system in May 2024 and produced the atmospheric detection announced in December 2025, is one data point in what will become a large statistical sample of rocky exoplanet atmospheres. The telescope is still early in its operational life. It is expected to operate for at least 20 years, accumulating a dataset of rocky planet observations that will dwarf what was possible before its launch. What the TOI 561b result has done is set the baseline. The first clearly confident rocky planet atmospheric detection in the ultra-short period class is a planet the model said could not have an atmosphere. Future detections or non-detections of atmospheres on similar worlds will be interpreted against this baseline. Is TOI 561b unusual? Is it typical? How do the atmospheric properties of these worlds correlate with stellar age, planetary mass, orbital distance, or composition? Those questions can only be answered by a large sample. JWST is building that sample, and the first result from the sample said, "Recalibrate your expectations." The fact that JWST is the tool that made this discovery points toward what the coming decades of planetary science will look like. The telescope is in the early years of what is expected to be at least a 20-year operational life. Its cryogenic coolant, which keeps its instruments at the temperatures required for infrared operation, was carefully managed during launch and initial operations to maximize the amount available. Current estimates suggest the telescope has enough coolant for significantly longer than its nominal 10-year mission. Combined with the absence of significant degradation in its instruments over the first years of operation, the scientific community expects JWST to continue producing data well into the 2040s. Over that time, the sample of rocky exoplanet atmospheres that have been studied will grow from a handful to potentially hundreds. The distribution of atmospheric properties across different planet types, stellar environments, orbital configurations, and ages will become statistically meaningful. What is now a single surprising data point, TOI 561b, will eventually be one entry in a database large enough to identify patterns. Are atmospheres on ultra-short period planets correlated with stellar age, with planetary mass, with the volatile content of the host star? Do they follow a distribution that matches revised atmospheric loss models, or do they continue to confound predictions? These questions cannot be answered from one observation. They require the sample that JWST is building. The TOI 561b result is the first data point in what will become a population study of rocky planet atmospheres across the galaxy. Its value is not only in what it tells us about this specific world, it is in how it resets the expectations for every world that follows it in the survey. Before JWST, This question could not be asked. Not because the question was hidden or because no one had thought to look for atmospheres on ultra-short period rocky planets, but because the instrumentation required to detect an atmosphere on a world like TOI 561b simply did not exist until a few years ago. The atmosphere of a planet like this does not announce itself loudly. It does not glow visibly. It does not alter the star's light in ways detectable by an ordinary telescope. To find it, you need to measure the thermal emission of the planet's dayside with enough sensitivity to detect the difference between a bare rock temperature and an atmosphere-cooled temperature. You need infrared instruments operating at wavelengths that Earth's own atmosphere absorbs, so ground-based observatories cannot see them. You need stability and cold operating temperatures that earlier space telescopes could not maintain. You need continuous monitoring capability that allows you to watch 4 complete secondary eclipses in a single unbroken observation run. The Hubble Space Telescope, launched in 1990, was transformative for astronomy in countless ways, but its instruments were not optimized for this kind of measurement on rocky worlds. Previous infrared space telescopes could characterize the atmospheres of hot gas giants, planets many times the size of Jupiter, with thick hydrogen-helium envelopes. Detecting the far subtler signal of a volatile-rich atmosphere on a planet only twice Earth's mass required a new generation of tools. JWST was designed, in part, to make exactly this measurement possible. Its primary mirror is 6.5 meters across, almost 3 times the diameter of Hubble's. Its NISPEC instrument, the near-infrared spectrograph used in the TOI 561b observation, covers wavelengths from roughly 2.7 to 5.1 microns, a range that includes the thermal emission peaks of rocky planets at these temperatures. Its location at the L2 point, combined with its massive sunshield, keeps the instruments cold enough to detect the faint infrared signatures that reveal a rocky planet's heat. The observation program that produced the TOI 561b result monitored the system for more than 37 continuous hours, capturing 4 complete secondary eclipses. This kind of extended, uninterrupted monitoring is a specific capability of JWST. The telescope can hold a target with extraordinary stability for long periods, accumulating signal without the interruptions that would plague a ground-based or lower orbit facility. Lead author Joanna Teskey noted after publication that this is a discovery only Webb could make. The instrument, the orbit, and the observing strategy came together to produce a detection that was not possible before December 2021, when JWST launched on Christmas Day from the Guiana Space Center. This places the discovery in a specific context. JWST has been operating for approximately 3 years. In that time, it has already found the strongest evidence yet for an atmosphere on a rocky planet in a place where no one expected to find one, using a technique that previous facilities could not have executed on this kind of target. The implication is not just that TO 561b has an atmosphere, it is that JWST has just demonstrated the capability to find atmospheres on rocky worlds that previous science had written off entirely. And the first result from using that capability on an ultra-short period rocky planet is a world that contradicts the models. Whatever the second result is, and the third and the 10th, they will come from a universe that has already told us the first place you looked broke what you thought you knew. That is not a small thing. The open questions about TOI 561b have a specific structure that is worth examining carefully. They are not gaps in the data that arose from insufficient observation. They are gaps that the initial detection opened by showing that the existing framework was incomplete. They are questions that did not exist until the answer to a previous question revealed that more questions lay beneath. Before JWST observed TO 561b in 2024, the open question was, does this planet have an atmosphere? The models said no. The observation was designed to test that prediction. The answer was yes. That answer immediately opened a second-order set of questions. What is the atmosphere made of? How does it survive? What does the night side look like? These are questions that the existing framework could not predict in advance, because they depend on physical processes that the framework did not include at sufficient fidelity to produce a correct prediction. The atmospheric composition question requires more JWST observations targeting specific molecular absorption features. The telescope can do this in principle. The required integration times are long, and the signals are faint, but the technique is within JWST's capabilities. Future programs targeting TOI 561b at different wavelength ranges may begin to reveal the molecular inventory of the atmosphere. The night side condition question is harder. The night side is, by definition, not visible during a secondary eclipse observation. Measuring the night side temperature requires a different observational approach. Tracking the brightness of the system as the planet moves from the night side transit configuration to the day side eclipse configuration, building a phase curve that maps temperature around the entire orbit. This is even more observationally demanding than the secondary eclipse measurement. The survival mechanism question is the deepest open problem. It requires not just more observations of TOI 561b, but better theoretical models of how magma atmosphere systems operate on geological timescales. It requires laboratory measurements of volatile solubility in magma at extreme temperatures and pressures. It requires modeling the rate at which the magma ocean is replenished by the planet's interior heat. It requires understanding how the stellar wind interacts with an atmosphere continuously supplied from below rather than maintained as a fixed inventory. These are research programs that will take years. What the discovery has done is show us where the knowledge runs out. The gap in the map has been identified. The territory beyond it is now the territory of science. The broader scientific context of the open questions about TOI 561b includes a parallel research program that JWST is conducting on a completely different category of potentially habitable worlds. The TRAPPIST-1 system, a red dwarf star approximately 40 light-years from Earth, hosts 7 roughly Earth-sized planets. 3 of them orbit in the habitable zone, the range of distances from the star where liquid water could theoretically exist on a planetary surface. These 3 worlds, TRAPPIST-1e, FEF and G, have attracted enormous scientific attention as the most accessible potentially habitable rocky worlds known. JWST has already observed several of the inner TRAPPIST-1 planets for atmospheric signatures. The initial results for the 2 innermost planets, TRAPPIST-1b and c, suggest they do not have substantial atmospheres. They appear to be bare rocks consistent with the models that predicted the innermost planets in this system would be stripped. The question of whether the habitable zone planets, farther from the star and somewhat more protected, have atmospheres remains under investigation. TOI 561b is not a potentially habitable world. Its surface is melted rock at temperatures incompatible with any known biochemistry, but the discovery of its atmosphere is relevant to the TRAPPIST-1 research program because both investigations are probing the same fundamental question: how do rocky planets retain or lose their atmospheres in different stellar environments? The models that predicted bare rock TRAPPIST-1 inner planets and the models that predicted a bare rock TO 561b share underlying assumptions about atmospheric escape rates. If one of those assumptions is wrong for TOI 561b, it may need revision for the TRAPPIST-1 planets as well. The findings from extreme lava worlds like TOI 561b and the findings from potentially habitable worlds like TRAPPIST-1 are part of the same research program. They are testing the same physics from different extremes. The atmospheric detection is the headline, but the questions it opens are in some ways more scientifically significant than the detection itself. The temperature measurement tells the team one thing: something is redistributing heat on TOI 561b's day side. The most consistent explanation is a thick, volatile-rich atmosphere. But the measurement does not tell them what that atmosphere is made of. The spectrum captured by NISPEC shows the planet's total infrared emission across a range of wavelengths. It tells you how much heat the planet is emitting and at what temperatures. It does not, at this level of analysis, reveal the molecular fingerprints of specific gases. Water vapor absorbs infrared light at particular wavelengths. Carbon dioxide has its own signature. Sulfur dioxide has another. Each molecule leaves a specific imprint on the spectrum if it is present in sufficient quantities. Detecting these features requires more observations, longer integration times, and careful comparison of the spectrum with models of different atmospheric compositions. The team has stated they are analyzing the complete dataset to construct a temperature map around the planet and to better constrain the atmospheric composition. Future observations targeting specific molecular absorption features could in principle identify what the gases are, but those results have not yet been published. The confirmed detection is the existence of the atmosphere. The chemistry of that atmosphere remains open. The night side of the planet is equally unknown. If the atmosphere is thick enough and the winds strong enough, heat could be redistributed from the day side to the night side. A thick atmosphere with vigorous circulation could warm the night side enough to keep its surface molten as well. The planet would then have a global magma ocean on both hemispheres, not just the sunlit one. But this depends on wind speeds and atmospheric capacity that current data cannot constrain. Whether the night side is molten or solid, what its temperature is, what its surface looks like, these questions are entirely open. The mechanism by which the atmosphere has survived for 10 billion years is also unresolved. The outgassing hypothesis is the leading candidate. The magma ocean continuously replaces the gas stripped by the star, maintaining a dynamic equilibrium. But the rate at which gas is produced by the magma ocean depends on the volatile content of the rock, the temperature of the melt, the circulation patterns within the magma, and the rate at which the ocean is replenished from the planet's interior. None of these parameters are directly measured. They are inferred from models. Whether the inferred rates are consistent with 10 billion years of atmospheric survival is a question those models are still working to answer. There is also the broader question of whether this planet is exceptional or representative. Are there other ultra-short period rocky worlds that have similar atmospheres hidden behind the assumption that they should be stripped bare? The models that said TO 561b could not have an atmosphere were applied universally to this class of planets. If those models are wrong for TOI 561b, how many other worlds have been misclassified? JWST is already designed to test this. The same observational approach that detected TOI 561b's atmosphere can be applied to other ultra-short period rocky planets. Whether those observations reveal similar discoveries, or whether TOI 561b turns out to be genuinely unusual within its class, is a question that the next several years of JWST observations may begin to answer. What the current data cannot answer is important to hold clearly. The confirmation is of an atmosphere. The composition, the nightside conditions, the survival mechanism, and the representativeness of this planet among its class are all, as of the time of this observation, open. And that is not a weakness of the science. It is what science looks like when a new capability points at the universe for the first time and finds something it did not expect. The answer to one question becomes the opening of 5 more. That is the pattern. That is how knowledge grows. The phrase atmospheric escape, which appears throughout the scientific discussion of TOI 561b, has a specific physical meaning that is worth making concrete. Every molecule in a planetary atmosphere has a thermal velocity, a speed determined by its temperature. At higher temperatures, molecules move faster on average. The distribution of speeds within a gas is not uniform. Most molecules are near the average, but some are moving faster and some slower. In the high-energy tail of that distribution, there are always some molecules moving faster than the rest. A planet's escape velocity is the minimum speed needed to leave the planet's gravitational pull entirely. It depends on the planet's mass and radius. For Earth, escape velocity is approximately 11 kilometers per second. For a smaller world like TO 561b, with roughly twice Earth's mass but only 1.4 times its radius, the escape velocity is somewhat higher than Earth's, roughly 14 kilometers per second. At the temperatures in the upper atmosphere of a tidally locked planet close to a hot star, where extreme ultraviolet radiation is heating the gas to thousands of degrees, a significant fraction of the lighter atmospheric molecules, hydrogen, helium, oxygen atoms can achieve velocities exceeding the escape velocity. They leave, they are gone. This process is called Jeans escape, or more broadly, hydrodynamic escape, when the outflow is vigorous enough that the upper atmosphere effectively flows away from the planet. On TOI 561b, this process has been ongoing for 10 billion years. The star has been bombarding the upper atmosphere with high-energy radiation throughout that time. The escape flux, the rate at which molecules are lost to space, has been relentless. The models that predicted a stripped atmosphere said The escape flux exceeds the rate at which the planet can replenish the atmosphere. The total atmospheric inventory would be depleted within a few 100 million years. The JWST measurement says the atmosphere is still there. Either the escape flux was lower than the models calculated, or the replenishment rate was higher, or both. The balance that the models said would tip decisively in favor of stripping apparently did not. Something about the specific combination of this planet's geology, its interior volatile content, its outgassing rate, the character of its stellar environment, has maintained the balance for 10 billion years. That is the correction the universe is making to the models. Not by telling us what the right answer is, by showing us that the answer we had was wrong, and leaving us to find out why. The relationship between model revision and scientific progress is subtle and worth examining in the context of this discovery. When a model fails, the immediate response might be to question the reliability of models in general. If the atmospheric loss models were wrong about TOI 561b, why trust any model? This response is understandable but incorrect. Models are tools for encoding current understanding. They produce testable predictions. When a prediction fails, it does not mean the model was useless. It means the model identified the limit of understanding at the time it was built. The failure itself is scientifically valuable because it points specifically to where knowledge was incomplete. The atmospheric loss models for ultra-short period rocky planets were built from the best available understanding of the relevant physics. That understanding was genuinely good. The models correctly predicted that these worlds would be exposed to intense radiation. They correctly calculated the rates of photoionization and atmospheric heating. They correctly identified the escape velocity threshold. The framework was not wrong in its mechanisms. It was incomplete in its accounting of the replenishment side of the balance. This is a meaningful distinction. An incomplete model that identifies its own gaps through testable predictions is not a failed model. It is a model doing its job. The gap between the prediction and the observation is precisely the information needed to improve the model. The revised model, when it is built, will incorporate what TOI 561b has revealed, that under some conditions, magma ocean outgassing can sustain an atmosphere against intense stellar stripping for geological timescales much longer than previously assumed. The revised model will produce different predictions for other ultra-short period rocky worlds. Those predictions will be tested. The process continues. This is how science works. TOI 561b is not a refutation of planetary science. It is planetary science functioning correctly. To feel what the detection of this atmosphere means, it helps to understand what studying exoplanet atmospheres looked like before JWST existed. The first confirmed exoplanet atmosphere detection came in 2001, when the Hubble Space Telescope measured sodium absorption in the atmosphere of HD 209458b, a hot Jupiter, a gas giant many times the mass of Jupiter, orbiting very close to its star. Hot Jupiters became the workhorses of early atmospheric characterization for a simple reason. They are large, they have massive gas envelopes, and their atmospheric signals are relatively easy to detect compared to smaller worlds. The detection of atmospheres on smaller planets in the super-Earth or Earth-size range, was far more difficult. The signals are smaller, the atmospheres are thinner, the planets emit less infrared light in total. The first tentative hints of atmospheres on non-giant exoplanets were ambiguous for years, difficult to distinguish from stellar noise or systematic instrumental effects. TARPist-1, a red dwarf star about 40 light-years from Earth, has a system of 7 roughly Earth-sized planets, 3 of which orbit in the star's habitable zone. These planets have been studied extensively because they represent the best current candidates for finding rocky worlds that might have conditions suitable for life. JWST has observed several of them. The results so far have been mixed. Some of the TRAPPIST-1 planets appear to have no significant atmospheres. The innermost ones look like bare rocks. Others remain under study. 55 Cancri E, another hot super-Earth with an ultra-short orbital period, was studied by JWST before TOI 561b. The results from 55 Cancri E suggested a possible atmosphere, but the data were described by researchers as, in the words of one scientist, messy and weird. The signal was real but difficult to interpret cleanly. TOI 561b is the result that changed the terms of the conversation. The data are not messy. The team's word was confident. The temperature discrepancy is large enough and the model comparison clear enough that the atmospheric conclusion is robust in a way that earlier measurements were not. This means something specific for the field. The era of rocky planet atmospheric characterization has effectively begun, not as a promise or a projection, as a confirmed result published in a peer-reviewed journal based on data from a facility that is currently operational and growing its dataset. The first clearly confirmed result is a world where the atmosphere should not exist, orbiting a star old enough to have watched our entire solar system form and develop from scratch, sitting above a global ocean of molten rock, replenishing itself through processes that our models did not adequately account for. That is the first result. The universe has opened the era of rocky planet atmospheric study by immediately informing us that the models we were planning to use need revision. The implications for the search for atmospheres on other rocky exoplanets are not speculative. They are a direct logical consequence of the TOI 561b result. The scientific community has been developing a priority list of rocky exoplanets to study with JWST for atmospheric characterization. That list was built around criteria that reflected the existing models, target worlds in the habitable zones of nearby stars where temperatures might allow liquid water, target worlds large enough to have held onto gas over planetary timescales. Avoid worlds so close to their stars that atmospheric escape would have stripped them clean. TOI 561b fails every criterion on that list. It is not in a habitable zone. It is not large enough to have been expected to retain a gas envelope. It is exactly in the category that the priority list was designed to deprioritize, and it has the most clearly confirmed rocky exoplanet atmosphere detected so far. This suggests the priority list needs revision, not abandonment. The worlds on the existing list are still important targets, but the list was built on models that have just been shown to be incomplete for at least one specific type of planet. How far that incompleteness extends, whether it applies only to TOI 561b's specific combination of parameters, or to a broader class of worlds, is precisely the question that follow-up observations will investigate. What the result has done is open a new category of scientifically interesting targets, ultra-short period rocky planets that were previously dismissed as atmosphereless. These worlds are observationally accessible. They transit their stars frequently, which makes eclipse observations practical. They are nearby on the scale of exoplanet surveys. Many of them have well-measured masses and radii from previous surveys. The observational infrastructure exists. The targets are known. The scientific motivation has just become considerably stronger than it was 12 months ago. The question is now how many of the worlds previously dismissed as bare rocks are actually hiding atmospheres that the models never predicted. The question of whether TOI 561b is representative or exceptional within its class has significant consequences for how scientists plan future observations. If TOI 561b is genuinely unusual, if it represents a rare combination of circumstances that allowed an atmosphere to persist in an environment where almost no other planet of its type could sustain one, then the discovery is scientifically valuable, but its implications are limited. Finding one extraordinary case in a large population does not overturn the statistical expectation. If TOI 561b is representative, if there are many ultra-short period, rocky planets with similar ages and compositions that have similarly maintained atmospheres against the model's predictions, then the models require substantial revision and the prioritization of future observations needs to change significantly. Distinguishing between these two possibilities requires a larger sample. A few more confirmed atmospheric detections on similar worlds would indicativeness. A large number of confirmed bare rocks with TOI 561b as an outlier would indicate exceptionalism. The critical variables to test are likely age and composition. TOI 561b's 10 billion-year-old host star is not common in current exoplanet surveys. Most well-characterized exoplanets orbit younger stars simply because younger stars are more common and better studied for planet searches. But finding and characterizing ultra-short period rocky planets around old metal-poor stars is now a scientifically motivated priority that the TOI 561b result has created. If old, alpha element-rich stars like TOI 561 preferentially host rocky planets with persistent atmospheres, That would be a finding of enormous significance. It would suggest that the initial volatile content set by the star's composition plays a decisive role in whether a planet can maintain an outgassing cycle over 10 billion year timescales. It would connect the chemistry of the early universe to the long-term atmospheric evolution of rocky worlds. That is a testable hypothesis. JWST is the instrument to test it. The models are the thing. The models are why the discovery is genuinely disturbing rather than merely surprising. When scientists build a model of how rocky planets retain or lose their atmospheres, they are encoding everything they understand about the relevant physics into a mathematical framework. They include the rate at which the star delivers high-energy photons to the top of the atmosphere. They include the rate at which those photons ionize and heat the atmospheric gas. They include the planet's escape velocity, the speed a gas molecule needs to reach to leave the planet's gravitational grip. They include the temperature profile of the atmosphere and how it affects the thermal velocity of different gas species. They build in uncertainties and test the model against known cases. These models are not guesses. They are built from first principles, from well-understood atomic and molecular physics, tested against observations of planetary systems where we have enough data to evaluate them. They represent the current collective understanding of atmospheric physics. Those models predicted that a planet with TO561b's properties, its mass, its orbital distance, its stellar environment, its age, should not have an atmosphere. The planet has one. One of two things is true. Either the models are missing a physical process that is relevant here, something that the existing framework did not include, or the models have the physics right, but the initial conditions wrong. Perhaps this planet formed with a much larger volatile inventory than the models assumed. Perhaps the magma-atmosphere exchange is a more effective replenishment mechanism than the models accounted for. Perhaps there is a feedback between the stellar irradiation and the surface outgassing that stabilizes the atmosphere in ways current frameworks do not capture. The team does not know which of these is the explanation. The result has generated more questions than it has answered. That phrase appeared in the published commentary about the discovery, and it was not used in a disappointed sense. In science, generating more questions than answers is often the mark of a genuinely significant result. It means the observation has reached into territory where existing knowledge runs out. The revision required by this discovery may be modest. Perhaps a single parameter in the outgassing rate calculation needs adjustment. Or it may be substantial. Perhaps the entire framework for modelling atmospheric loss on tidally locked super-Earths close to old stars needs to be rebuilt from different starting assumptions. We do not yet know how deep the correction needs to go. What we know is this. There is a planet 280 light-years from Earth that has broken the rules. It broke them cleanly with a clear signal detected by the most powerful space telescope ever launched, documented in a peer-reviewed paper, and confirmed by 4 independent eclipse measurements in a single observation run. The universe has presented the field with a clear correction. Your models are incomplete. Here is a data point you cannot explain. That is the appropriate response to a good scientific result. Not distress, not crisis, not crisis, but clarity, a clear identification of the limit of current knowledge, with a specific example that marks exactly where the knowledge runs out. TOI561b is that limit. The history of planetary science is full of moments where the expected turned out to be wrong, but this specific type of wrongness, a model failure at the level of a factor of 10 in timescale, is worth examining on its own terms. When models fail by a small factor, it often means a parameter was slightly off. A reaction rate was measured imprecisely. The physical constant had an uncertainty that needed to be reduced. These failures are corrected by refinement. When models fail by a large factor, by an order of magnitude or more, it often means the model was missing something entirely. Not a poorly calibrated parameter, but an absent physical process. A mechanism that was not included because it was not known to matter. The outgassing replenishment hypothesis, that the magma ocean continuously restores the atmosphere, may be the missing mechanism. It was known before the TOI561b discovery. The concept of outgassing is not new, but the rate at which it operates on a global magma ocean, at the temperatures and pressures of a planet like this, over the timescale of 10 billion years, was not adequately modelled. The process was known, but its quantitative significance was not properly accounted for in the atmospheric loss calculations. If this is the missing piece, the correction to the models is specific and tractable. It requires better laboratory measurements of volatile solubility in magma at extreme conditions. It requires better modeling of how the magma-atmosphere exchange rate depends on temperature, pressure, and composition. It requires integrating those rates into the existing atmospheric escape framework. This is hard work, but it is defined work. The discovery has pointed at the gap clearly enough that the research community knows what needs to be done. If the outgassing hypothesis turns out to be insufficient to explain the full discrepancy, if the rates simply cannot be high enough to sustain the atmosphere for 10 billion years even with revised parameters, then the missing mechanism is something else, something not yet identified. And that is a harder problem, because it means the carried conceptual framework is missing not just a poorly quantified process, but an entirely unrecognized one. Either outcome advances the understanding. The first requires refinement. The second requires something closer to a conceptual expansion. Both are valuable. Both are the kind of advance that can only come from an observation that breaks the model cleanly and unambiguously. The question of whether the models can be revised to account for TO5561b, or whether a new conceptual framework is needed, connects to a broader issue in exoplanet science. Models of atmospheric escape are built around a relatively small number of well-understood physical mechanisms. Photoionization by stellar extreme ultraviolet radiation, thermal escape driven by atmospheric heating, stellar wind interaction with the planetary magnetosphere. These mechanisms are real and well documented. Their rates have been measured in our solar system and calibrated against observations of other planetary systems. But these mechanisms were calibrated primarily against the kinds of worlds that have been well studied: gas giants, hot Jupiters, and the few rocky worlds in our solar system. Applying them to a 10 billion year old ultra short period rocky world above a global magma ocean is an extrapolation. The calibration dataset does not include anything like TOI 561b. When models are extrapolated beyond their calibration range, they can fail in ways that are difficult to anticipate from within the original framework. The failure mode may not be in the mechanisms themselves, but in how they combine at conditions that have not been tested. The interaction between magma outgassing and atmospheric escape at TOI 561b's combination of temperature, age, and stellar environment may produce emergent behavior that neither mechanism alone would suggest. This is the kind of problem that requires new data rather than simple recalibration. TOI 561b is the first data point in the new regime. More data points from other old ultra-short period rocky worlds will be needed to characterize the behavior in this regime and build the models needed to describe it accurately. This is exactly what JWST is positioned to provide, not just for this one planet, but for the population of worlds that share its broad characteristics. The question of what TOI 561b means for the broader population of planets like it is not abstract. It has direct consequences for how scientists plan future observations. There are thousands of known exoplanets. A significant fraction of them are rocky planets orbiting close to their stars. A subset of those are ultra-short period planets with orbital periods shorter than one Earth day. Most of these have been characterized in terms of their sizes, masses, and approximate densities. Most have never been examined for atmospheres because the assumption was that planets in this category would not have them. That assumption was built into the prioritization of JWST's observing time. Resources are finite. The telescope's schedule is filled with programs selected through a competitive peer review process. Programs targeting atmospheric characterization of ultra-short period rocky planets were not a high priority because the expected result was a bare rock. Why spend valuable observing time to confirm what the models already predicted? TOI 561b changes the calculus. If a planet like this, which should have been a bare rock by every metric the models used, turns out to have a thick atmosphere, then the category of worlds dismissed as atmosphereless requires re-examination. Not all of them, perhaps not most of them, but some of them, perhaps a significant fraction of them, might be hiding atmospheres that the models never predicted. JWST has the capability to test this. The same secondary eclipse technique that found TOI 561b's atmosphere can be applied to other ultra-short period rocky worlds. The observations are demanding, requiring long continuous monitoring runs, but the telescope is operational, the technique is validated, and the scientific motivation is now considerably stronger than it was before December 2025. If subsequent observations reveal that multiple ultra-short period rocky planets have atmospheres, the implication cascades further. It suggests that the physical processes keeping these atmospheres alive, the outgassing replenishment cycle, the magma-atmosphere exchange, are more robust and more widespread than models assumed. It suggests that rocky planets in general may be more geologically active, more volcanically productive, more capable of sustaining gas envelopes in extreme environments than the current theoretical picture acknowledges. This matters for the search for atmospheres on potentially habitable worlds. The methods used to detect atmospheres on hot lava worlds close to their stars are related to the methods used to search for biosignatures on cooler, more Earth-like worlds farther from their stars. If the baseline models are wrong for the extreme cases, they may need revision for the moderate cases too. Understanding atmospheric physics on worlds like TOI 561b, where the processes are operating at extreme scales and are therefore easier to detect, informs the understanding of atmospheric physics on worlds where the signals are more subtle. TOI 561b is not a habitable world. It is not a candidate for life. It is a lava planet with a magma ocean and an atmosphere made from cooked rock vapor, orbiting 40 times closer to its star than Mercury orbits the Sun. Nothing about it suggests a place where biology could operate, but it is an extreme test case, a natural laboratory operating at conditions we cannot reproduce anywhere in our solar system, and the laboratory has just returned an unexpected result that the textbooks did not contain. The specific phrasing that emerged from the discovery team is worth examining carefully, because the language scientists use to describe results is chosen deliberately. Lead author Joanna Teska of Carnegie Science said after publication, "What's really exciting is that this new dataset is opening up even more questions than it's answering." That sentence contains a specific intellectual stance, not disappointment that the discovery left so much unexplained, not frustration that the composition remains uncertain and the survival mechanism is unknown. The word used was exciting. The opening of more questions than answers is described as the exciting part. This is the appropriate scientific response to a result of this quality. A discovery that fully explains itself is a minor result. It fits within the existing framework, adds a data point, and confirms what was expected. A discovery that breaks the existing framework, that cannot be accounted for by the current models, that raises second-order questions faster than it answers first-order ones. That is a major result. That is a discovery that will generate years of follow-up work, that will revise textbook understanding, that will change the questions asked about an entire class of objects. Co-author Anjali Piette of the University of Birmingham said, "We really need a thick, volatile-rich atmosphere to explain all the observations." The phrase "really need" is doing specific work. It is not saying the atmosphere is one possible explanation among several equally likely alternatives. It is saying the data are not consistent with the alternatives. The bare rock model was tested against the data and failed. The thin rock vapor model was tested and failed. Only the thick, volatile-rich atmosphere model matched the measured temperature. The atmosphere is required by the data. The team also noted explicitly that this is a discovery only Webb could make. That statement situates the result historically. The capability that produced it did not exist before 2021. The discovery is not the result of scientists having missed something for decades. It is the result of a new tool enabling a measurement that was physically impossible to make before the tool existed. These framings matter. They tell you how to interpret the result correctly, as a confident detection, as a framework-breaking observation, and as the first result from a new era of rocky exoplanet atmospheric characterization. There is something worth noting about the way the discovery team communicated uncertainty in their published results. Scientific papers are precise documents. Every claim is qualified with appropriate caveats. Results are presented with error bars that quantify the measurement uncertainty. Model comparisons are shown explicitly. with the data and the competing models plotted together so readers can see for themselves which model fits and which does not. The TO561b paper showed 3 model comparisons: a bare rock surface with no atmosphere, a thin rock vapor atmosphere, a thick volatile-rich atmosphere. The data clearly favored the thick volatile-rich atmosphere. The other 2 models predicted a planet significantly brighter than what was measured. The conclusion was that the data are inconsistent with a bare rock and consistent with a substantial atmospheric envelope. That is not a claim that the atmosphere has been directly imaged or that specific molecules have been detected. It is a claim that the temperature measurement requires a physical explanation, and the most consistent explanation is the presence of a thick atmosphere. The confidence in the detection comes from the quality of the temperature measurement and the failure of the alternative models to fit it, not from a direct molecular inventory. This precision in how the result is stated reflects the honesty that good science requires. The team did not overstate. They did not say the atmosphere has been fully characterized. They said the data are consistent with one model and inconsistent with 2 others. That is the correct framing, and it is the framing that will hold up as subsequent observations build a more complete picture. The scientific community accepted the result at this level of confidence. Published in a peer-reviewed journal. Reviewed by experts in the field who assessed the methodology and agreed the conclusions were supported by the data. That is the standard by which the result stands. Every few centuries, science encounters a discovery that forces it to revise what it thought it understood at a fundamental level. These revisions are not failures, they are the mechanism by which knowledge advances. The geocentric model was not wrong because astronomers were foolish. It was wrong because it was the best model available with the available data, and when new data arrived it required revision. The steady-state model of the universe was not wrong because cosmologists were inattentive. It was replaced by the expanding universe model because the data required it. Each revision carries a specific structure. There is a prediction derived from the best current understanding. There is an observation that does not match the prediction. There is a gap between what was expected and what was found, and from that gap, the next generation of models grows. TOI 561b is a gap, a planet 280 light-years away, twice Earth's mass orbiting its star. Every 10.56 hours, tidally locked, covered on its sunlit hemisphere by a global ocean of molten rock, wrapped in a thick volatile-rich atmosphere that should have been stripped away within the first few 100 million years of its existence, orbiting a star that is 10 billion years old. Every one of those facts is verified. The stellar age is derived from the star's chemical composition, a well-established method with small uncertainties. The orbital parameters are measured precisely from transit timing. The planet's size and mass are measured from transits and radial velocity data. The temperature, and therefore the atmosphere, is measured from 4 JWST secondary eclipses, with a result the team described as confident. The gap between the predicted bare rock and the confirmed atmosphere is not a matter of interpretation or methodological ambiguity. It is a direct conflict between the model's output and the telescope's output. The model says no atmosphere. The telescope says atmosphere. One of them must be revised, and it is not the telescope. This is how planetary science recalibrates itself. A new capability arrives, Webb. It points at a world the old models said was understood. TOI 561b should be bare. The old models are found to be incomplete. New observations expand. New theory is built. The field updates. What is specifically disturbing about this particular gap is its scale. It is not a small correction. A planet surviving with an atmosphere for 10 times as long as the models predicted is not a rounding error. It is a factor of 10 discrepancy between the model's timeline and reality. Something fundamental about the physical processes involved has been missed, and whatever that something is, it has been operating continuously on this planet for longer than Earth has existed. That is not a small thing to have missed. The phrase "most disturbing planet in the universe," which the title uses, requires honesty about what it means and what it does not mean. The universe contains objects far more violent than TOI 561b. Black holes are consuming entire stars. Supernovae are detonating, releasing more energy in seconds than the Sun will release in its entire 10 billion year lifetime. Neutron stars are generating magnetic fields so intense that the energy density warps spacetime. By the standard of physical violence, a tidally locked lava world 280 light-years away is modest. The disturbance in the title is a different kind of disturbance. It is cognitive rather than physical. It is the specific discomfort that comes from a model being broken clearly, publicly, and irreversibly, from the universe presenting a result that conflicts with the best current understanding in a way that cannot be explained away or softened or attributed to measurement error, from the recognition that something important was missing from the picture, and that finding out what it was will require years of work that the current generation of scientists may not fully complete. This is the disturbance that the discovery of TO561b produces. Not danger, not violence. The specific intellectual disturbance of a well-established framework meeting an observation it cannot account for, and having to begin the process of revision. The universe does not care about the models. It operates according to its own physics, which may or may not match human frameworks at any given level of approximation. When the mismatch is revealed, the appropriate response is not distress but inquiry. What is the universe doing that the model did not predict? What mechanism is operating here? What does it tell us about the broader class of objects this world belongs to? Those are the questions TOI561b has opened. And the disturbance, properly understood, is the productive discomfort of science encountering its own limits and being forced to expand them. The phrase "the most disturbing planet in the universe" is a title, and titles are designed to compel attention, but the substance behind the title is not hype. It is a specific, scientifically grounded observation about why this planet is genuinely unsettling to the people who study it. The disturbance is of a particular type. It is not the disturbance of danger or violence. It is the disturbance of a clean, confident prediction meeting a clean, confident observation, and the two not matching. Predictions are the currency of science. They are what elevates science above mere description. A model that only explains data already collected is not a model. It is a description. A model that makes predictions about data not yet collected, and those predictions can be tested and verified or falsified. That is science. The atmospheric loss models for ultra-short period rocky planets made a prediction. The prediction was testable. JWST tested it. The prediction was wrong. This is not a failure of the field. It is the field working correctly. The prediction was the best available understanding at the time. The test was the best available measurement capability at the time. The mismatch is new information, specifically the kind of new information that advances understanding faster than confirmation would. Confirmation of what was expected is progress in quantity. A clean, specific falsification, one that points at a missing physical process rather than measurement error, is progress in kind. It changes the structure of what is understood rather than just filling in more detail within the existing structure. TOI561b has changed the structure. Ultra-short period rocky planets are no longer confidently predictable as bare rocks. The question of whether and how they retain atmospheres has been reopened, with the specific new answer that the field did not have before May 2024. That is what science looks like when it is working, and the fact that a telescope pointed at a planet 280 light-years away for 37 hours measured a temperature that should have been predictable, and found that it was not, is a reminder that the universe is under no obligation to cooperate with human frameworks. It never has been. That is why we keep looking. Come back to the number. The number that started all of this, 4,900 degrees Fahrenheit expected. 3,200 degrees Fahrenheit measured. The gap between them is 1,700 degrees, and that gap is the entire story. In May of 2024, JWST pointed at a star 280 light-years away and stared at it for 37 continuous hours. It watched the star and a small planet orbiting it. It watched the planet disappear behind the star 4 times. It measured the brightness of the system with and without the planet's infrared contribution. It calculated a temperature. The temperature was wrong. Not dramatically wrong. Not impossibly wrong. Wrong in the specific, measurable, reproducible way that means something real is happening on the planet that the models did not account for. The telescope did not fail. The planet is not cooperating with the prediction. An atmosphere is there, and then, as the investigation continued, Every additional fact about TOI 561b added another layer to the disturbance. The proximity of the orbit, the ultra-short period, the tidally locked condition, the permanent day side locked in an eternal, motionless noon, the surface temperature exceeding the melting point of rock, the global magma ocean covering the sunlit hemisphere, the atmosphere being produced by that magma ocean, maintained by the same process that should have been overwhelmed and stripped away long ago, and then the age, the 10-billion-year-old star. The atmosphere that has survived by some mechanism the models did not adequately describe, for roughly twice the age of our entire solar system. Each layer makes the previous one worse. That is the structure of this discovery, and it is the structure the title promises. The most disturbing planet Webb has found is not disturbing because it is violent or dangerous. It is disturbing because it is wrong. Wrong in the way that good science recognizes and investigates, systematically, specifically, reproducibly wrong. Wrong in a way that points directly at something the current understanding is missing. The universe keeps doing this. It keeps taking the best available models and presenting data that the models did not predict. It keeps finding ways to operate that the frameworks have not accounted for. TOI 561b is one version of this pattern. A world 280 light-years away, sitting above a global ocean of liquid rock breathing an atmosphere from its own melting surface, doing it for longer than anything in our solar system has existed. And finally, after 10 billion years of this being noticed by a telescope launched 3 years ago that stared at it for 37 hours and found a number that was wrong, 3,200 degrees Fahrenheit, when the model said 4,900. That gap, that single gap is what disturbs, not because the gap is physically dangerous, because the gap is a message the universe is telling us, again, clearly, in numbers we can quote and repeat and test. You do not yet understand what you are looking at. We are listening. Good night. The closing image of this discovery is not the planet itself. It is a number. 3,200 degrees Fahrenheit. That number, measured on a clear night in May 2024 by an infrared spectrograph operating in deep space, is the precise location where the current understanding of rocky exoplanet atmospheres runs out. On one side of that number is a bare rock at 4,900 degrees, which is what the models predicted. On the other side is the universe, returning a temperature almost 2,000 degrees cooler and waiting for science to explain the difference. The difference has been explained, provisionally, as an atmosphere, a thick, volatile-rich atmosphere above a global ocean of molten rock on a tidally locked world orbiting its star every 10.5 hours. Maintained by the outgassing of that magma ocean against the stripping force of a star it has been circling for 10 billion years. Every layer of that description is real. The tidal lock is a physical consequence of the orbital period and the stellar mass. The magma ocean is a physical consequence of the dayside temperature and the surface composition. The outgassing is a physical consequence of the chemistry of the melt. The atmosphere is a physical consequence of the outgassing. The survival over 10 billion years is a consequence of whatever balance between loss and replenishment the planet has maintained since before our solar system existed. And none of it was expected. None of it appeared in the predicted output of the models that described this class of planet before JWST looked. That is what the discovery of TOI 561b means. Not just that one planet broke the rules, that a new capability pointed at the universe for the first time in this specific way, and the first thing the universe returned was a clear correction to what we thought we knew. The correction is in the number 3,200 degrees Fahrenheit, when the models said 4,900. The gap between those two numbers is the edge of what was understood, and on the far side of that edge, there is a planet that has been there for 10 billion years, waiting to be found.